What if the strongest wind energy was not found on hills or offshore platforms, but drifting quietly high above them? Far up in the sky, the air moves faster and more steadily, yet almost no turbines reach it. That is starting to change. A new class of floating wind machines uses giant helium balloons to lift generators toward constant high-altitude winds. One Chinese system even aims to hover at 1,500 meters and power thousands of homes. This video follows how these airborne turbines work, what they promise, and which hard questions they still need to answer. The sky joins in. Around the world, wind power has grown into one of the main pillars of clean electricity, yet a basic problem remains. The wind at ground level is changeable. Sometimes there is so much wind that turbines must be shut down, and grid operators struggle with too much power. At other times, the air falls quiet, and output drops far below expectations. Energy storage helps, but batteries and other solutions are still expensive and slow to build at a massive scale. One strategy tries not only to manage this volatility, but to avoid much of it. Instead of relying on gusty surface winds, engineers look higher into the atmosphere, where air currents move more smoothly. Near the ground, buildings, forests, and hills act like brakes. They slow the wind and stir it into turbulence. As altitude increases, these obstacles matter less, and the wind usually becomes stronger and more stable. Physics amplifies this effect. Wind power scales with the cube of speed. When wind speed doubles, the available energy rises by a factor of 8. Some studies have suggested that high-altitude winds could, in theory, supply many times the world's current energy demand, even though only a fraction of that could ever be harvested. Wind technology has already been climbing towards this resource. Over recent decades, turbines have gained much taller towers and longer blades. New models in places like eastern Germany are approaching heights of 350 meters or more, almost matching city landmarks. As heights increase, engineering becomes harder, transport grows more complicated, and opposition often rises because tall towers dominate the landscape. At some stage, it starts to seem more attractive to ask a different question. Instead of building ever higher masts, could wind technology simply float in the sky where the air is already strong and steady? At this point, airborne wind energy systems enter the story. Rather than stretching towers ever higher, they use flying structures to reach strong winds without a fixed mast. All of them combine two elements, something that flies and captures energy from the air, and a generator that makes electricity. In ground generation designs, the generator stays on the ground. A wing or kite is attached to a tether and steered through large loops. As it pulls the tether out, the tension spins a drum linked to a generator, much like a giant yo-yo. When the line is fully extended, it is reeled in again with much less force, and the cycle starts over. In onboard or fly generation concepts, the generator travels with the aircraft. Several rotors are mounted on a frame. They spin in the wind, drive generators on board, and send power down to a station on the ground through a cable. Both designs try to replace heavy towers with lighter flying structures that can move up or down to follow the best wind layers. The Chinese S-1500 system follows this second approach. Instead of one large generator, it uses 12 smaller modules, each designed for about 100 kilowatts. Together, they provide a rated power of roughly 1.2 megawatts. The frame and housing are made from carbon fiber, so the full unit weighs under a ton. It does not look like a kite or drone. It resembles a ring-shaped airship with a circular helium-filled shell that gives it buoyancy. Around this ring sit the rotors that face into the wind, while cables carry the produced electricity down to the ground station. The helium lift gives the S-1500 a special status among airborne designs. Because the ring itself floats, the system does not need constant motion to stay in the air. Classic kites and wings must fly fast patterns. When the wind is too weak or too strong, they have to be brought down. A buoyant turbine can simply hover and adjust its height, searching for a layer where the wind is strong enough but not dangerous. The S-1500 is intended to operate at altitudes of around 1,500 meters, where winds are often far more consistent than near the surface. The technology is still young, so the machine remains in a test phase. Earlier prototypes paved the way. A smaller S500 version reached heights of about 500 meters and produced around 50 kilowatts. Later designs grew larger and more capable. Recently, an S1500 prototype completed trial flights in the Gobi Desert, although not yet at its full intended altitude. Engineers focused on stable flight, safe control, and performance under different wind and temperature conditions. When compared with conventional wind turbines, the numbers look mixed at first. Modern onshore turbines commonly reach 5 or 6 megawatts of rated power, far above the S1500's 1.2 megawatts. Yet yearly energy output depends more on capacity factor than on peak power. Onshore turbines often achieve around 2,000 full load hours per year, which equals a capacity factor near 25% and yields roughly 12,000 megawatt hours for a large unit. Airborne systems seek higher factors by following steadier high-altitude winds. Earlier buoyant projects offer clues to what might be possible. High-flying turbines from the company Alteros reported potential capacity factors between about 60 and 75%, more than double typical onshore values. If a system like the S1500 could reach a capacity factor around 65%, its 1.2 megawatts of rated power would translate to roughly 6,800 megawatt hours per year. That is still only about half the output of a large modern onshore turbine, but it comes from a much lighter machine without a tall tower or deep concrete foundation. This difference becomes important when the economics are considered. By avoiding heavy towers and foundations, airborne systems could cut material needs by up to 90% compared with standard wind turbines. Some manufacturers argue that, combined with steadier production and faster construction, this might reduce electricity costs by as much as 30% per kilowatt hour. Their portability also opens new locations. Equipment can be packed, shipped with normal trucks, inflated on site, and raised using winches. Studies of airborne wind suggest a global potential ranging from around 14 to more than 100 gigawatts, although the higher figures come from industry groups and must be treated with caution. One pattern appears again and again. Most of this potential lies in areas that are poor sites for conventional turbines, such as regions with weak surface winds, rough terrain, or little infrastructure. Rapid deployment also makes buoyant turbines attractive for disaster relief and other temporary tasks, where they can provide both emergency power and high platforms for communication antennas. Past attempts also show how difficult it is to turn airborne wind into a major power source. Alteros began with the goal of selling energy and carried out successful test flights in Alaska at heights of several hundred meters. The engineering worked, but helium became a stubborn obstacle. Gas slowly escaped through the envelope and had to be refilled, while global helium prices rose. Over time, operating costs climbed so high that the business of selling electricity no longer looked competitive. Alteros then shifted its focus toward using buoyant platforms mainly as flying cell towers and observation posts. Google's Makani project took a different path, but met similar limits. Makani built rigid wings with multiple small rotors along the edge, following the ground generation model. The wings flew complex patterns, pulling on tethers and generating power through ground-based generators. After more than a decade of work, the team demonstrated impressive control and technical performance. However, the machines were complex, maintenance was demanding, and the cost of each kilowatt hour remained higher than power from ordinary wind farms and solar parks, whose prices kept falling. Beyond cost, airborne systems must prove long-term safety and reliability. Automated control has to handle takeoff, changing winds, storms, and landing with minimal human input. Materials for envelopes and tethers must survive years of sunlight, rain, dust, and mechanical stress. Airspace rules need to protect aircraft from tethers, and communities must accept large balloons in the sky. These technical hurdles arrive even before social debates. In many regions, people already argue about the sight and sound of ordinary wind farms. Adding large balloons or looping wings to the same skies will demand clear rules, long test periods, and convincing safety records. For now, airborne wind looks less like a direct replacement for existing turbines, and more like an experimental tool that could serve specialized roles if it proves reliable and affordable in real conditions. Floating wind turbines are unlikely to replace classic wind farms, yet they may still claim a useful niche. Their strengths match places where normal turbines struggle: remote deserts, offshore platforms, scattered islands, and disaster zones that need fast, flexible power. As part of a wider renewable mix, airborne systems could act like mobile tools, moving where they are needed most and lifting communication antennas at the same time. As prototypes such as the S-1500 face real weather, real costs, and real rules, the coming years will show whether the sky can truly join the energy transition. Many will follow closely,